Okay, so we're going to talk about a new section now. And that section is called Viscous Flow. And really what it is we're going to talk about first flow within pipes. And in particular, fully developed laminar flow in pipes. Those two different vocab words now that we need to really define and talk about. And we're going to start with laminar. We've talked about laminar in the past, but let's talk a little bit more about it, especially in the context of pipe flow. So within pipes, laminar and transitional flow and turbulent flow have pretty distinct. They look pretty distinct. For example, laminar flow. We know for laminar flow that streak lines, streamlines, and path lines all overlap, right? So streak lines equal streamlines, which equal path lines. These all overlap because laminar flow is steady, right? The path that a particle would take in laminar flow is the same that another particle would take when released from the same spot. So transitional flow looks like laminar flow sometimes. So I would call this intermittently true. Other times it looks turbulent, right? And what turbulence is it's chaotic flow, right? It's chaotic flow, and you have mixing in all three dimensions. So even if you have a two-dimensional flow, you're going to end up with flow velocities in the, for example, remember when we had infinite plates in with flow in between two infinite plates, where we had z being the plane in and out of the paper. Well, with turbulent flow, you'll even have mixing in velocity into and out of the page, even if the only velocity you have is parallel to the page, right? So flows exist, and then beyond turbulent, we have compressible flow start to matter, in which case we have a different kind of situation. But flows exist on this on the scale of laminar to turbulent, and really what this scale is it's really well indicated by Reynolds number. So Reynolds number increasing in this direction. So right about 2100 for a Reynolds number for pipe flow, and that, remember, Reynolds number is equal to density times our velocity times our diameter divided by mu, where this is our diameter of our pipe. This is the average velocity of pipe. And density and viscosity, you guys know. So 2100 is when laminar flow ceases, and roughly, right? It's not like you tick from 2,900 or 2,099.9 into 2,100, and suddenly now you start getting transitional flow. It can vary a bit, and we'll talk about that in just a second. And transitional flow will exist until about 4,000 for a Reynolds number, and beyond that we start to get increasingly turbulent flow. Now, like I said, the exact numbers depend heavily on conditions of pipe, vibrations, the conditions of the entrance. This is remarkably true. I'm going to show you guys some. Well, eventually we're going to talk about the Moody chart, and one of my professors in college, his grad school project, I believe it was his master's, although it could have been his PhD. I can't remember exactly. His master's project was to measure something called the frictional flow or friction coefficient for very, very smooth pipe. And what he was trying to do is he was trying to push laminar flow to as high of Reynolds numbers as he could. So he was trying to, well past 4,000, get laminar flow, and that requires very, very smooth pipe. You have to begin your pipe with very, very smooth entrances, and you can't have vibrations. And so he would have to actually do his experiments at night because people walking in the hallway would create enough vibrations that it would trip turbulent flow. And and so he would get erroneous results, right? And so to that end, right, entrances, lots of things make a difference in terms of what actually ends up being turbulent. We've done this before, but if we draw flow going in this direction into an entrance like this of a pipe, it turns out, right, we know fluid coming around this corner, it can't make this corner at 100%. And so we usually get a recirculation region at the top and bottom like that. And then the flow eventually smooths out, and we get a lot of circulation and turbulence due to these rough edges or sharp edges here. And the amount of time it takes for these entrance effects to damp out and for us to get a uniform velocity profile is something called the entrance length, LE. So for a smooth pipe, this can be as small as 0.6 times the diameter, or it can be as large as 120 times the diameter. And like I said, this is called the entrance length. So since fluids can't take a corner, right, very well, we can, if we make a rounded corner, we can get very nice, easy entrances here, and we can actually have a very small entrance length that is not very long, because our flow just naturally is eased into the direction it needs to go into. We can model this, so that we're not going to ask you to really do this much in class, but just so you know, you can model the length of the entrance length. So we make a non-dimensional parameter called LE over D, and for laminar flow, this is roughly equal to 0.06 times the Reynolds number. And for turbulent flow, this is equal to 4.4 times, not times 10, 4.4 times the Reynolds number to the 1/6 power. So something to note about both of these is that as you increase the Reynolds number, you increase the entrance length. What does this mean? Well, remember Reynolds number, we're going to write this again. I want you guys to be able to memorize this. Reynolds number